So I work on trying to understand how the universe works at the very basic level, the most basic level we can find. So when you try in your everyday life to try and work out how something works, what you're actually doing is you're looking for what I call hidden structures. For example, you take something like your cell phone, your smartphone, and it's a complicated object, and you might wonder how it works. Well, what you can do is go in and actually take it apart. You'll void the warranty, but that's okay. And you go in, and what you find is that it's made of tiny little electronic components. And those electronic components are actually moving around a certain kind of particle we know that's called the electron. And that's where the name electronics comes from. So if you know the actual rules of how to put those things together, you can actually make your smartphone, or you could make various other electronic devices as well. So there are people like myself who actually, for a living, try and do this sort of thing, not just for, say, a cell phone or its components, but asking what, say, your hand is made of, or the chair you're sitting in, or the planet Earth, the sun, the stars, the entire universe. And so using various kinds of instruments and observations and experiments, we've been able to probe deeper and deeper over the years, and we now know that the matter that we're made of and that we see around us is actually made of tiny little elementary particles. And elementary particles interact with each other via the forces of nature, but we've also discovered that those forces of nature themselves actually operate by exchanging elementary particles as well. They're actually particles of force that are exchanged by the particles of matter. And you may have heard this year that there was big news, a major announcement in this story. The Large Hadron Collider, the LHC, a huge experiment in Europe, has actually uncovered a Higgs boson. And that particle's job is to interact with the various elementary particles and give them the masses that we observe. So this exciting picture is analogous to the one I showed you for the cell phone. We have the components, and we have the rules of particle theory, as it's called, by which these all operate and give rise to the various things. Now, we actually think that we've only just scratched the surface of finding this quantum world, the hidden structure of our world. Let me give you 3 examples of the puzzles we're still working on. So what I did is I gathered the particles up into the patterns that they tend to form, and we don't know where those patterns come from. We know how to describe the particles, but we don't know where the patterns come from. When you see patterns in science, you look for a hidden structure. So that's one of the things. Also, we now know that there's a huge amount more matter out there than just the things that I was just talking about. That stuff is called dark matter. We don't know what it is, and we'd like to be able to get it and experiment with it and figure out what it is. And then the other thing I'd like to tell you about is the fact that the force of gravity, perhaps the most familiar force we know, when you get down to the quantum level, it actually doesn't operate according to those rules of particle theory. So given that gravity is actually about the shape of space and time, as Einstein taught us, in working out what the quantum story of gravity is, which we call quantum gravity, we hope to get to grips with questions like, are there particles of space and time itself, and how do they fit together? What are the rules? So this leads us to things like studying where it all began. 13.7 billion years ago, the Big Bang, we know matter and energy as we understand it was created, but also space and time itself. So those are the sorts of things we study in this quest. Also, we have things that are around us today, such as black holes, which are very important clues. They're actual holes in space that we'd like to actually understand. Also, the newly discovered dark energy, which is the tendency of space all through the universe to accelerate its expansion. So scientists are working on these kinds of things, trying to understand what we think is now the case, that there's not just hidden structures of matter and energy, but also of space and time. So the question is, what are the rules? And there are many approaches to this, and one of them is one that you may have heard of called string theory. And so it's one of many approaches, and we don't know if it's right yet. We've not finished developing the theory, but it's given us some really exciting, tantalizing hints. I'd like to tell you about a few of them. So one of them is simply that you take away the idea of looking for a tiny quantum particle, and you look instead for an extended object, a string, which can vibrate. And that actually gives you some exciting opportunities, because, for example, it would say, if we'd missed that hidden structure by not looking closely enough, we wouldn't realize that many different kinds of particles are just different vibrations of the same string, which is a really exciting possibility and a huge simplification. So that's one of the ideas. The other thing that's really exciting about string theory is that one of those particles it describes is actually the missing quantum of gravity that we've been trying to understand. And then the other thing is that strings actually, instead of wanting just to move in the dimensions, the 3 space dimensions that we're familiar with, actually seem to want to move in higher dimensions. So we have this idea then, what would it mean for our world if this were anything to do with our world, and we don't know that yet? Here's a way that our world would arise from that. You would have our world, and then one of the hidden structures would be hidden chunks of space-time that are not visible, those extra dimensions. And then the various particles that we see in the world would come from being vibrations of strings, and those patterns we saw that we can't explain come from the fact that the strings can probe and feel the shape of those internal dimensions. So one of the things then is, can we actually test this? This is a lovely idea, but how do we confront this with real experiments and observations? Because we're doing science here. And that's the hard thing. We think that the energy you need to probe the tiny enough scales to see the strings if they're there is more than we can hope to get anytime soon. But what we can do is we can look for the consequences of those hidden structures. We can look for how those things show up in physics that we can get access to. So that's why we study things like dark matter, black holes, dark energy, and we also look at remnants of the early universe, the cosmic microwave background with satellites. And importantly, we look for clues from the various kinds of particle physics experiments like the LHC. So one last thing then is a new thing that's been going on. String theory may turn out to be useful in other areas of physics. There are new kinds of experiments that start out, say, with our friends the electron, and actually show that in certain circumstances, the electrons interact in a way that give you completely new, weird kinds of behavior. And there are models that show that string theory is actually the best way, in some circumstances, using the rules of string theory, you can actually explain that sort of behavior. So this gives this exciting possibility that there's real experiments you can do with these electrons that will help us shape the rules for what string theory is. And you might go, well, okay, that's going to give us maybe some fancy new kind of electronics that we can make a better cell phone with. But I'm saying that those rules may actually be the same rules we're looking for to see if string theory can help us with these bigger questions. So at the end of the day, the hidden structures of the universe we're looking for may one day be right under our noses. Thank you.